Chapter 9, Lesson 1. In this chapter we'll take a look at molecular geometries and then something called bonding theories. So what we're going to be looking at in general are the shapes of the various molecules possible in the bonding. The shape of a molecule is very important for us to talk about because very often the properties of the molecule depend in large part on its three-dimensional shape. So especially when you're talking about molecules that interact with the body, the shape of it essentially determines how it acts within the body. So we will be taking a look at many of these shapes. Here are a few examples that we'll delve a little deeper into as we go along. So the question, what determines the shape of a molecule, essentially are the electron pairs around the central atom, what are called the bonding pairs, and then the non-bonding pairs. In this case, for example, if you take a look at ammonia, NH3, if you draw its Lewis structure, what you'll see, this is NH3, what you'll see is that ammonia has a non-bonding pair around it, then three bonding pairs. These together, repelling one another, will determine the shape of the molecule. And our assumption will be that the electron pairs will repel and then be placed as far as possible from each other. So because the electron pairs, electrons are negative, electrons will repel each other, situating themselves to be in distant portions, as far as possible, essentially. So we're going to have to define something called electron domains as we go along. And then simply put, the electron pairs around the central atom will be called electron domains. So if we have a double bond or a triple bond, and all the electrons are shared between the two atoms, then we will count that as one electron domain. What we mean here is this is called one electron domain, and so is this. If you had a triple bond, that will be one electron domain. So think of electron domain as area of electrons. Since we can say all these electrons are in the same area, this constitutes one electron domain. So for this molecule we have 1, 2, 3, 4 electron domains is the idea. And these 4 electron domains will then influence the overall shape of this molecule. And the theory that will allow us to predict the shape of molecules will be something called VSEPR. From here it looks like it's VSEPR, but don't let your friends pronounce it VSEPR. Make sure VSEPR is the way we call it in the business. And again, this means the valence shell electron pair repulsion theory. So it's all about the electron pairs repelling one another. And a statement that we'll make here about this theory is that the best arrangement of a given number of electron domains is the one that minimizes the repulsions among them, which means the electrons will spread out as far as possible in 3 dimensions. So a very famous molecule, probably one of the most famous shapes, will be this shape. And as you see, if you can think of this, we have the electron domains. We have 4 electron domains here, and these 4 electron domains are spreading themselves out as far as possible to form this shape, this tetrahedral, as we'll call it, shape. A good way to visualize this, in fact, if you take a bunch of balloons, blow them up, and begin tying them together, if you were to tie 4 balloons together at the center, they will, in fact, assume this shape here, as you'll see. And that's essentially the same thing that happens on the molecular level. Let's take a look at the 5 possible electron domains, shapes in general. And in fact, we're going to go into each one of these in detail, but I would like to notice here, take a note here, and take a look at what are called the bond angles. So these numbers, as we go down here. If you take a look, if we have 2 electron domains around the central atom, the gold here represents the central atom, and then these around are electron domains. If you have 2 electron domains, we're going to assume that around a circle we have 360 degrees. So if you divide that in half, you get yourself 180 degrees. So with 2 electron domains, you get yourself 180 degrees. If you have 3 electron domains, then 360 divided by 3 gives you 120. So for 3 electron domains, you get 120. if you keep doing this, if you tie 4 balloons together, we just talked about this, you get yourself this tetrahedral shape. Now, the 4 balloons, essentially on paper, the way we draw this, for example, this could be said to be CH4. If we draw CH4 on paper, what you'll see is it looks like CH4 essentially exists as a square, but remember, this is only in 2 dimensions on paper. When we spread this out in 3 dimensions, these will spread apart from one another a little bit. So you would assume to divide 3 or divide 360 by 4, this would give you 90 degrees here, but in fact the real shape is not 90 degrees because these essentially electron domains spread out a little farther, and in 3 dimensions you get yourself 109 degrees, 109.5 to be exact. So 4 electron domains gives you 109.5 degrees. So if you keep tying balloons together, if you tie 5 balloons together, for example, you'll see that you get yourself an interesting arrangement that looks like this. And here we have 2 possible bond angles. As we'll see, the central atoms, or the central, not atoms, but electron domains, what we'll call the equatorial domains, create 120 degrees between them, and then the top and the bottom, what we call the axial domains, will form 90 degrees. So for 5, you get both 120 and 90. And if you tie 1 more balloon, for 6, you get yourself just 90 everywhere. So these bond angles will be important as we go along. We'll mention them, but we'll take a look at each one of these shapes in much more detail as we roll along. So the way to count how many electron domains we have is to first draw the Lewis structure, and then the geometry that will determine the electron domain will be the one that corresponds to that many electron domains. So for example, if you take a look at the Lewis structure of NH3, here we have 1, 2, 3, 4 electron domains, and in 3 dimensions 4 balloons will arrange themselves in this way. And we call this tetrahedral. Now the reason for the name is because tetrahedral forms a 3-dimensional figure with 4 sides. In fact, it's kind of like a pyramid, but it really a tetrahedral type pyramid. So we have a face here, it's facing us, one here, one behind, and then one on the bottom. So a 3-dimensional figure with 4 sides called a tetrahedron. And each one of these essentially electron domains points to a corner of this tetrahedron, and that's why the name tetrahedral. Now if you take a look, the shape itself of the molecule will be a little different than the shape of just these electron domains. So because there will be bonding and non-bonding electron domains as we go along. But the general idea is count how many electron domains on the Lewis structure, and then spread them out as far as possible and give that a name. So once we see the electron domain geometry, which we decided was tetrahedral, then we'll have to take a look at the molecular geometry. Now, since there is a pair of electrons essentially situated on the top, this pair of electrons, because it creates a cloud of negative charge, will repel these bonded pairs of electrons, which also recall are clouds of negative charge. And in this case, essentially think of this cloud as repelling and then pushing down on the other 3 electron domains. And that's why if you take a look at the molecule itself, the molecule looks like this, and we call this trigonal pyramidal. And we'll go into the details of each one of these. But the final one we want to take a look at essentially is something called molecular geometry, the one that only takes account or only cares about the atoms bonded around it, but we will have to assume an invisible pair of electrons up here that's influencing the bonding in this way. So within each electron domain there may be more than one molecular geometry. So our first task will be to take a look at the electron domains, and then from that we'll be able to determine the geometry. For example, if all of the atoms are bonded to the central atom, if all of these outside here are atoms, then we'll call this tetrahedral. If one of them is an empty pair, we'll call it trigonal pyramidal. If 2 of them are empty, we'll call it bent. But notice all of them are based on 4 electron domains around the central atom. And these are 3 examples of possible molecules. This is methane, ammonia, and good old H2O. So we'll begin with the simplest. We'll actually get into each one of these in a little more detail. The simplest arrangement will be called linear. And in a linear arrangement, you got yourself essentially just 2 domains, and both of them are bonding. So on the left side, it'll tell you how many electron domains you have. On the right side, how many bonding domains. So in this case, if you only have 2 and both of them are bonding, you get yourself a linear arrangement. And if you recall, the bond angles of this was 120 degrees. This is just a half of a circle, essentially. And then a note down here about if you only have 2 atoms, then the only way those 2 atoms can come together, essentially, is in a linear fashion. So we don't show it here, but 2 atoms will always give you a linear arrangement, or linear molecular geometry. In this case, we have 3 atoms, which gives you also linear, but that's because you only have 2 electron domains. Technically, there are not any electrons up here or down here that are influencing the bonding of these 2. These are actually absent, is kind of the idea. So because these are absent, you get yourself a little bit of difficulty. There it is. You get yourself a linear arrangement. The second, take a look here. The second possibility is if you have yourself 3 electron domains, and there are 2 possibilities. If all 3 are bonding, then you get yourself this picture. And this picture is called trigonal planar. And the reason why we call it trigonal planar technically is because we have 3, which constitutes the trigonal portion of it. 3 atoms are on the outside, and they lie in a plane. So if you were to look at it, you'd see that it's kind of like a triangle. They essentially lie in a plane. Say this portion of the triangle is looking toward us. So we call this trigonal planar. If you have yourself 3 electron domains, but only 2 of them are bonding, meaning 1 of the electron domains is empty, as you see up here, then you get yourself a bent shape. So again, this electron domain influences these bonding domains, bending them down. So think of it this way. This would be a bent arrangement. If you have 4 electron domains, here we have 4 electron domains, if all 4 of them are bonding, then we get this tetrahedral shape that we've talked about. All 4 of them go to different corners, giving you minimal repulsion, maximum arrangement, and you get yourself tetrahedral. This is the famous tetrahedron, the figure with 4 sides, essentially, down here. If you have 3 of the domains, if 3 of them have atoms on them, and 1 of them is a pair of electrons, then you get yourself this interesting arrangement. You get yourself trigonal pyramidal. Now, trigonal again means you have 3 atoms, 1, 2, 3, but pyramidal means these atoms are not lying in a plane. And the reason they're not lying in a plane is because we have an extra pair of electrons influencing them, pushing them down, if you would, repelling them. A famous example of this is ammonia. This is NH3 that we spoke of before. This extra pair up here pushes the rest of the atoms down, creating this trigonal pyramidal shape. If then you have yourself 4 main electron domains, but only 2 of them are bonding, the other 2 are not bonding, in other words, you have yourself 2 empty pairs of electrons, then you get yourself a bent shape. Now if you take a look, this bent shape essentially reflects the tetrahedral shape. Just take off this atom and take off this atom, and then you get yourself what's left is the bent shape. Remember, these atoms are essentially replaced by electrons, empty electrons, which repel and give you this shape. And the famous shape that is bent, of course, is dihydrogen monoxide. So we have ourselves 3 possibilities with a tetrahedral arrangement of electrons. So why don't we do a little example? And the example is using the VSEPR model, predict the electron domain geometries and molecular geometries of the following. So we have carbon monoxide, a tin, a trichloride. Technically this is a polyatomic ion, so we'll have to consider this. And then finally we have O3, which is ozone, good old ozone. So let's try all 3 of these. So the first thing to do is to go ahead and write or draw the lowest structure. So we have carbon monoxide. Remember, for carbon we have 4 valence electrons. From oxygen we have 6 valence electrons, for a total of 10 valence electrons. So we'll put carbon and oxygen with a bond between them. Let's go ahead and count until we get to 10 total. So we get 2 in the middle here, 3, 4, 5, 6, 7, 8, 9, 10. At this point we cannot add any more, so we will ask essentially carbon to share both of its electrons, one on the inside, another one on the inside, and we get ourselves a picture that looks like this, with a triple bond in the middle and a pair of electrons on every atom on the outside. So now let's go ahead and get the electron domain geometry. Domain. Now in this case, both the electron domain geometry and the molecular geometry will be the same. And the reason being, anytime you have yourself 2 atoms, the only thing that can happen is the atoms can be arranged in a linear fashion. This is actually the easiest arrangement, technically. So if you want to technically think about this, the 2 electron domains that we have are around, because there's really not a central atom. If we think of oxygen as the central atom, we have 1 electron domain on the right, 1 on the left, so we have 2, and 2 corresponds to a linear arrangement. If we think of carbon as the central atom, exactly the same thing happens. You have 1, 2 electron domains, and that gives you a linear geometry, is the idea. Alright, let's try the second molecule. The second molecule is tin SnCl4 with a -1 charge. If you take a look at tin essentially sits in the same group as carbon does, so tin should have 4 valence electrons. So 4 for tin, 7 for each chlorine, we have 4 of those, and then 1 more because of the negative charge. So 7 times 4, we get 28, plus another 4 for tin, and that gives us 32, and so 33 electron valence electrons in this case. Actually, I see what I did. 33 is a bit strange. I see what I did. This should actually be a 3, should it not? This is where I'm going wrong. So this is actually a 3. That works a little better. I was being worried about an odd number of electrons, and I was calling for a little bit of problem. Okay, so in this case we get ourselves a 21 plus 4, 25, 26 electrons total. So we'll have to arrange 26 electrons around the central, around the whole entire molecule. So let's go ahead and put tin in the middle, as it is the less electronegative element. Let's put the 3 chlorides around the outside. We have 26 electrons total. We got 2, 4, 6 in the middle, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So every element has an octet of electrons. We are ready for the geometries. The molecular geometry, or not the, let's begin with the electron domain geometry, and then we'll do the molecular geometry. The electron domain geometry will be based on how many electron domains we have around the central atom. So in this case, 1, 2, 3, 4. So 4 corresponds to tetrahedral. Now, not all of these are bonding. In fact, you have yourself a non-bonding pair up here. So pretend that this is invisible now in terms of the rest of the atoms, and the rest of these then will bend down, if you would. The rest of the chlorine atoms on the outside will bend down and technically give you this sort of arrangement right here. Because you can't see the top pair of electrons up at the top, this portion will disappear, giving you essentially a trigonal pyramidal arrangement. So our molecular geometry will have to be trigonal pyramidal. pyramidal. And that's really, recall that's the molecular geometry that we really care about, so trigonal pyramidal. Right, let's try one last one before we finish off here. And that last one was ozone, O3. So each oxygen brings 6 to the bond. We have 3 of those for a total of 18. So if we take a look, we have an oxygen in the middle and 2 oxygens around the outside. Give us a picture. It looks kind of like this. Let's get a little better representation here in the middle. Make this bond nice, and there it is. So we have a 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Looks like the central oxygen does not have enough, so we'll ask this electron pair to come inside. This becomes a double bond, and then let's go ahead and get rid of these. So this is one possibility. Now anytime you have equivalent bonds possible on both sides, we said that it's actually the double bond's going to exist on both sides, giving you resonance. So we actually have to show, in this case, the idea that the double bond can also be on the right side, and then completing the Lewis structure gives us this, and then we'll put a double-headed arrow to represent resonance. Remember, you have to watch for resonance, as some of these molecules are represented better by 2 shapes or 3 shapes. Now we can get on to the electron domain geometry and then the molecular geometry. So the electron domain geometry, if you take a look, each one of these show 1, 2, 3 electron domains around the central atom. 3 gives us trigonal planar. And then we see that only 2 of them are bonding, and the other one up here is actually a non-bonding pair, which means whenever you have a trigonal planar arrangement, this is how the atoms arrange, and because this one becomes invisible, you get yourself technically a bent shape. So the molecular geometry will actually be bent. So feel free to try this with other molecules. If you follow this procedure where you first determine the electron domain geometry and then think of the lone pairs as disappearing but still influencing the rest of the bonds, then you can actually visualize your molecular geometry. And this will complete lesson 1 of chapter 9.